My name is Benno, and I will talk today about the concept of pseudo-complex numbers in general relativity. In April, the 10th of April of the last year, the Event Horizon Telescope presented the first image of the center of a galaxy M-Oytasech, and there we can see the shadow of a black hole and surrounded by a light ring. And how can we interpret this image? Well, let's have a look at the sketch here on the side. If the light beam comes close to the black hole, it is bended by the strong gravitational field and is absorbed inside the event horizon. But if the light beam comes distant to the black hole, it will be it can make a trajectory around it and can enter to some observer to some distant observer. What he will see is, if the light is approaching him, he will see the Doppler shift with frequency elevated, and it will appear more hot in the image. And on the other side, it is, if he looks on the other side where it goes other way around, it is a Doppler shifted to lower energies. This can be seen over here. So if we use the prediction of general relativity and we think that the black hole is surrounded by an accretion disk, then the general relativity predicts an innermost stable circular orbit, which is called ISCO. And the infalling matter, due to the strong gravitational fields, should stop at this stable orbit. And then we should observe a black region, but here will emerge the scattering of the light, which is bended by the strong electromagnetic field, by the strong gravitational field. And inside we will see the horizon. No? The radius of the innermost stable circular orbit depends on the spinning of the black hole. So if the spinning of the black hole is faster, the smaller is the distance of this innermost stable circular orbit. My motivation for introducing the algebraic extension with the numbers of the pseudo-complex numbers, I will motivate now. Well, in general relativity, a black hole mass collapses into a point. This is a singularity. No force can stop this collapse of mass. The event horizon leads to something coordinate singularities, so we need to make a transformation to a metric where we can treat the metric of the light which is inside the black hole cannot go outside. So the event horizon emerges, and this is characterized by the Schwarzschild radius. No information inside the black hole can reach an observer which is outside the event horizon. And this is somehow, from a philosophical point of view, not very convincing in general of a theory. And therefore, there had been done some algebraic extensions to the general relativity, and I will talk about one which is the pseudo-complex coordinates. Introducing the pseudo-complex coordinates, there appear a minimal length parameter, which does automatically a regularization. it is, if we are nearby, this minimal length makes somehow treat the high force momentum nearby these strong gravitational fields. And at large distances, the theory is nearly equal to the general relativity of Einstein. But to see differences caused by this nearby effect, we need observations in extreme physical situations because we are looking for small effects. In comparison to the other algebraic extensions, which one was introduced by Einstein also of a complex general relativity, only the algebraic extension of PC coordinates prevents unphysical ghost solutions in weak gravitational fields. So this is why these pseudo-complex coordinates are in favor for using the description of these algebraic extension now. And PCGR leads naturally to a repulsive additional term in the Einstein equation, and this can be interpreted as a dark energy term, and this eliminates the event horizon. Let's have a look at the field equation of Einstein. You see it here in yellow. We have the Einstein field tensor on the left side, and on the right side we have only geometric quantities. We have the metric tensor of the curvature, we have the metric scalar R, and we have the metric tensor G minu. So this part is only geometrical in nature, and the left part here emerges the energy momentum tensor where all the masses are involved. And this term here can be related to somehow dark energy contribution, which emerges with the introduction of the PCGR coordinates. So the theory of Einstein can be characterized that the mass tells the space-time how to curve, and the space-time curvature tells the mass how to move. And in PCGR, we have an extension to this. Mass curves the space and also changes the vacuum structure of the space itself, which can be interpreted as dark energy. You know? So PCGR contributes to the equation of motion, a term interpreted as dark energy, which is repulsive, which is important. So let's come to predictions of the PCGR. It predicts a maximal orbital frequency. This is important because if a black hole has an accretion disk, a dark ring should appear caused by this maximal orbital frequency. And this should be observed. Above a given spin of the PCGR black hole, no innermost stable circular orbit exists. So the accretion disk reaches the PCGR black hole and the disk is observed brighter. Now let me say something about the complex numbers in comparison to the pseudo-complex numbers. There you know, if you take the imaginary unit squared, it gives -1. And in the pseudo-complex numbers, the pseudo-complex imaginary unit squared gives +1. And we can describe it in two bases. One basis is rotated by 45 degrees. So here we have the relations which are related to these transformations. And with this, we can define the pseudo-complex metric, which is created by these pseudo-complex numbers, where we have a metric in the plus part and in the minus part. But we lead the symmetry that G mu needs to be G nu mu. The space-time is enlarged with a combination of a form momentum, where emerges the force velocity multiplied by this minimal length parameter. And we can calculate the length element. And what we see, this squared element needs to be positive or 0. So here emerges the force acceleration, which is related due to this relation, which needs to be bigger or equal to 0 with the minimal length. We have also a maximal acceleration due to this relation. I implemented a library where I can use the arithmetic for the pseudo-complex numbers. Here I have a sketch of an application which I I programmed a pseudo-complex calculator which can do these arithmetic things using this library for testing. And so let's come to the conclusion. General relativity versus PC general relativity. In extreme physical situations, near massive objects with strong gravitational fields, the description of the PCGR near the Schwarzschild radius leads to significant deviations from the general relativity predictions. With high accuracy, this can be observed in near future experiments, and the detection of gravitational waves opens a new window for observations of black hole and neutron star mergers in catastrophic astrophysical scenarios. The main reference I used is all included in this book of Peter Hess about the pseudo-complex general relativity. Thank you very much.
Okay, thank you. Okay, perguntas, questions.